One of the biggest reasons the clean energy transition feels harder than it should is because energy storage is still being treated as a single problem. In reality, storage is not one challenge, but two fundamentally different ones. When those challenges are confused, projects become inefficient, unreliable, and financially fragile. When they are separated and designed correctly, clean energy systems begin to work the way they were always supposed to. Modern energy systems need two distinct storage layers, not one. Not a compromise between technologies. Two layers that operate at different time horizons, serve different functions, and respond to different constraints. Ignoring this reality is one of the most common mistakes in clean energy design today. The first storage layer exists to handle volatility. Electricity is unforgiving. Supply and demand must match instantly, every second of every day. As renewable energy penetration increases, volatility increases with it. Solar and wind generation rise and fall based on weather, time of day, and season. Demand does not always cooperate. This mismatch happens on the scale of milliseconds to hours, and it must be managed continuously. This is where short-duration storage dominates. Batteries are the backbone of the first storage layer. They respond instantly, stabilize frequency, smooth power flows, and absorb rapid fluctuations that would otherwise destabilize the grid. Without this layer, modern grids with high renewable penetration would simply not function. Batteries are not optional at this level, they are structural. But volatility management alone does not solve the energy transition. It only keeps the system balanced in the moment. The second storage layer exists to address a completely different problem: imbalance over time. Renewable energy does not just fluctuate minute to minute. It fluctuates across days, weeks, and seasons. Some regions produce massive amounts of renewable energy at certain times of the year and very little at others. This creates long-term mismatches that short-duration storage cannot solve economically. This is where long-duration storage becomes essential. Hydrogen is the most prominent technology in this second layer because it allows energy to be stored in large quantities for extended periods. Hydrogen converts electricity into a chemical form that can be stored, transported, and used long after it is produced. This capability is not about speed. It is about endurance. Confusing these two storage layers leads to flawed design decisions. Batteries are criticized for being too expensive when used for seasonal storage. Hydrogen is criticized for being inefficient when asked to respond instantly to grid fluctuations. Both criticisms are valid and completely miss the point. Each technology is being judged outside the layer it was designed to serve. The first storage layer is about control. The second storage layer is about capacity. Control keeps the lights on. Capacity ensures energy is available when it is needed, regardless of when it was produced. A resilient clean energy system requires both. This layered approach becomes especially clear when looking at green hydrogen production. Electrolyzers sit at the intersection of both storage layers. On one side, they are sensitive electrical devices that require stable power input. On the other, they produce a long-duration energy carrier. If electrolyzers are connected directly to volatile renewable power without buffering, they experience rapid ramping, shutdowns, and unstable operating conditions. This accelerates degradation and increases costs. Batteries form the first storage layer that protects electrolyzers from volatility. They smooth power input, reduce ramp rates, and allow electrolyzers to operate closer to steady-state conditions. This improves efficiency, extends equipment life, and increases hydrogen output over time. Without this layer, hydrogen production becomes technically possible but economically fragile. Once hydrogen is produced, the second storage layer takes over. Hydrogen can be stored for weeks or months, transported to distant markets, or used when demand rises. This is what allows renewable energy to be shifted not just across minutes or hours, but across seasons and geographies. Batteries alone cannot perform this role at scale without becoming prohibitively expensive. Curtailment exposes the consequences of ignoring storage layers. As renewable capacity grows, grids increasingly waste energy because it cannot be absorbed at the moment it is generated. Batteries capture some of this excess, but only within limited time windows. Hydrogen absorbs surplus energy without immediate time pressure. When both layers are present, Curtailment drops dramatically and asset utilization improves. This improvement in utilization directly affects project economics. Energy assets generate value only when they are used. Idle capacity destroys returns. Hybrid systems that combine short duration and long duration storage operate more consistently across the year, making them far more attractive to investors. Financial markets understand storage layers even when public discourse does not. Banks and institutional investors are not interested in ideological debates about technology. They are interested in predictability. Revenue volatility increases risk. Uncertainty increases financing costs. Projects that rely on a single storage layer often struggle to demonstrate stable cash flows under real-world conditions. Hybrid systems, by contrast, can stack value streams. Batteries provide grid services, frequency regulation, and arbitrage. Hydrogen provides long-term energy supply, industrial offtake, and fuel diversification. Together, they reduce exposure to single market risk and improve overall project resilience. Designing projects around two storage layers, however, adds complexity. More components mean more interfaces, more dependencies, and more coordination challenges. Renewable generation, batteries, electrolyzers, grid connections, permitting timelines, offtake agreements, and financing milestones must align. This is where many projects fail, not because of technology, but because of execution. Execution discipline becomes critical in layered systems. Dependencies must be managed carefully. Delays in one component ripple through the entire project. Without structured planning, complexity turns into chaos. This is why professional developers rely on robust project management tools like Microsoft Project to manage schedules, critical paths, and interdependencies. At this scale, execution tools are not administrative conveniences. They are risk management instruments. Equally important is understanding how to design these systems in the first place. Many professionals entering the hydrogen space are experts in individual technologies, but lack exposure to integrated system design. They understand batteries or hydrogen in isolation, but struggle to connect them into coherent, bankable architectures. H2Hub at https://h2hub.renewable.com was created to address exactly this gap. It focuses on real-world green hydrogen project development, emphasizing how storage layers interact and how hybrid systems are designed, modeled, and executed. The objective is not to promote a single solution, but to build competence in systems thinking that aligns engineering decisions with economic and operational realities. The misconception that energy storage can be solved with a single dominant technology persists because it is simpler to communicate. But simplicity is not accuracy. The real world is layered. Grids are layered. Energy demand is layered. Storage must be layered as well. As the energy transition moves deeper into industrial decarbonization, the importance of this layered approach will only grow. Heavy industry requires reliability measured in months and years, not hours. Grids require stability measured in milliseconds. No single technology satisfies both constraints. Two storage layers are not optional, they are structural. The future clean energy system will therefore not be defined by a single breakthrough technology. It will be defined by architectures that intelligently combine fast response control with long-duration capacity. Systems that respect these layers will scale. Systems that ignore them will struggle. This video builds on the foundation established in the previous two episodes. Hydrogen versus batteries is the wrong question. Batteries optimize time while hydrogen optimizes scale. And the energy transition succeeds only when both are organized into distinct but complementary storage layers. If you want to develop the skills to design, model, and execute hybrid energy systems built around these principles, the tools and training at h2hub.renewable.com are designed for that purpose. And if you are managing complex energy or infrastructure projects, the Microsoft project tools linked in the description are the same platforms used across large-scale developments worldwide. Clean energy will not succeed through single-solution thinking. It will succeed through layered systems and disciplined execution.